All right, so it's a great pleasure to continue with our lecture today and have Eric Ramos from Stephen Institute of Technology. And we're going to hear about universality theorems for generalized.
Yeah, so thank you all for being here. Thank you to the organizers for inviting me to speak. This is really nice. I look forward to attending conference year after year after year. Yeah, so I accidentally gave this talk earlier today. So let me just say, for those of you who are at the earlier version, it'll largely be the same, but I do expect I'll go a little bit further than I got in that talk, because there I was aiming more maybe at an advanced undergraduate level, and here I think there are certain things I don't need to necessarily explain. So I do think I'm going to get further. So yeah, just so everybody.
Also, on that.
Yeah, exactly. And if I repeat any jokes, please don't call me out. Okay. Anyways, so today we're going to talk about generalized splines. Now, the word spline appeared in the previous talk, and so there's a nice little synergy there, which is entirely accidental, but not welcome. So what is a spline? So classically speaking, and when I say classical, I mean going back to like the 1800s. If you talked about splines in a mathematical context, you were talking about what were essentially piecewise polynomial functions, usually defined on polyhedron. Okay. And generally, it's like you have piecewise polynomials with some degree of kind of smoothness that is demanded on the intersection of kind of the pieces. So just imagine like, okay, I have this arc, maybe like this, nice arc. And I want to approximate this by like a piecewise polynomial function, which might look kind of like this. And so this was a tool that engineers and analysts used. But then kind of years later, in the 1980s, Valera and Rose kind of took the theory and realized that, like, okay, if we're studying these kind of piecewise polynomials and polyhedral complexes, there's actually a fair bit of algebraic geometry that's kind of working under the surface that the analysts were not necessarily equipped to deal with. So those two were the first two to treat the theory from the perspective of more of an algebraic / homological algebra. And what they realized was that, like, essentially the theory of splines was equivalent to like a certain, like, you could view it from the perspective of a certain labeling on the dual graph of the polyhedral complex you were working on. Now, of course, not every graph is the dual graph of a polyhedral complex. However, the labeling properties that were described in that context, there's no reason why we could not just apply them to any graph. And so was born the theory of generalized splines. It's like, let's take this thing that's very specialized over here and has all of this associated algebraic geometry, and let's just kind of generalize it in kind of the most natural way and see what kind of things we get. So let me write down definition. So first of all, for this talk, a graph is at most one-dimensional CW complex. I'm rather be very careful here and say finite CW complex. And just so it's clear, the reason I say at most one-dimensional is because I absolutely have given a talk in the past where I called it a one-dimensional PW complex, and somebody immediately raised their hand and was like, "Oh, so a single vertex is in the graph to you?" Like, all right. We're mathematicians, we're supposed to be precise. So at most one-dimensional finite CW complex. And the reason that I write it this way for any graph theorists in the room is because, like, essentially I am telling you that I am thinking about graphs as potentially having multi-edges and loops. Because why not? Okay. So what are a fixed ring, and S a set of ideals, and R, then an S labeled graph, or an S labeling, I should say, of a graph G is a function from edge set G S. So nothing terribly fancy here. I'm, as you might expect, an S labeling is literally me labeling the edges of my graph with ideals coming from S. So I'm usually going to denote this by something like alpha. Okay, so now we're ready for our final definition. Given an S-labeled graph, alpha, a spline on G alpha is an assignment of ring elements to the vertices G such that if, let's say, V is adjacent to W, then RV minus RW is in alpha of. Okay, so a spline on an S-labeled graph is an assignment of ring elements to the vertices of your graph, such that if two vertices happen to be connected by an edge, then I need the difference between those ring elements of those two vertices to be in the ideal of that edge. Just as like a nice little example you here. So perhaps let's say my ring, the integers. Let's say this is 2, 4, 3, 2, 3, 3. Okay, so as drawn here, this is an S-labeled graph. And now a spline would be an assignment of an integer to every vertex in such a way that if two vertices are connected by an edge, the difference is in the corresponding ideal. So, for instance, I believe I could do something like 5. This is 3. This is 9. This is 7, and perhaps these are both 4. So this is a perfectly valid spline on this edge label. Okay. Now, just because it might become important later, note the collection of splines on the alpha form an R module. Right? Because if I take two splines, then there is a natural way which I can add them, which is to say just add them vertex by vertex. And if you satisfied this kind of edge condition to start with, you're certainly going to satisfy it afterwards. And given an element of the ring, if I take a spline and I scale it by that element, then certainly I still satisfy the ideal condition, because that's kind of how ideals work. Okay, great. So this thing actually forms an R module, which is called the module of splines. And we will denote it very simply by capital R with a subscript. Questions about this practice? Premise? So just as like a cute little thing, and possibly trying to draw the connections between where splines came out in the last talk and what we're talking about here. So it turns out that there's a family of graphs called GKM graphs, which are naturally associated to certain toric varieties. And the idea is that, oh, it turns out that the module of splines is related with the equivariant cohomology of that toric variety. So the module of splines, like, again, for an arbitrary graph, is something that generalizes this object, which is very heavily rooted in algebraic geometry.
But you could actually have no spline, right?
So great question. So you are always guaranteed for at least one dimension, as it were, of splines to exist, because if I assign the same value to every vertex, then the differences are all zero. And that will land in any label. So this is a great point, which is kind of what I want to do next. So note something to note the facts. Number one, this ring is not ever going to be kind of empty, as you always can take trivial splines of all the same value. So you're never going to be in a situation where the only allowable spline, I guess, unless you're dealing with the zero ring, which I personally don't know. I don't know if I consider that a ring. I like my ones and my zeros to be distinct from each other. Call me crazy. So yeah, you can always take trivial splines. Now, fact number two, and this again, this is just like making sure that our perceptions are aligned here, is that the ring of generalized splines is always living inside of a free module. I mean, I'm really not saying anything profound here. I mean, this is essentially just by definition. This is always living inside of a free module. So in particular, if R happens to be a PID, say, then RG alpha is free necessarily. Although, just to be, if R is not a PID, then very much so the ring of the module of splines is not a PID or not free in general. Like you can absolutely cook up examples pretty easily where this thing is not going to be free. Okay, so a lot of the early research in this area was related with the following. Two questions. So number one is what do the minimum generating sets look like? I mean, in the case where R happens to be a PID, we're asking about bases. But of course, in general, the best you can do is talk about the minimum generating sets. And number two, if R happens to be a K algebra, then what can we say dimension of I said at the beginning that, compared with the talk I gave earlier today, there are certain things that I think I can take for granted and not have to explain. And when I gave this talk earlier today, I stopped to be like K algebra, where K is a field. And I'm like, today, no, don't need to do it. Right now, we all know. No question, K is a field. Yeah, so what can be said about this dimension? Okay, so let me give you a result that's in this vein. And it considers the following. So let G equals Cn be a cycle. Let R be this polynomial ring. And let S be comprised of ideals of the form explicitly defined. Okay, so a few things about these hypotheses. First of all, as we said at the beginning, splines really did originate from this place that we were looking at piecewise polynomials. And still to this day, when people talk about generalized splines, oftentimes they are talking about generalized splines over polynomial rings, or at least quotients of polynomial rings. So from the perspective of the theorem I'm about to state, like this choice of R was not considered controversial. Number one. Number two, the fact that we are kind of seemingly limiting our allowable labels to be in this form, it turns out is not really that much of a limitation. In the paper, they describe like if you're taking labels in any collection of homogeneous ideals, essentially the theorem that I'm about to state, you can always reduce it to the case where the ideals look specifically like this. There's like a degree reduction process, which you can lower the degrees of labels. So both of these hypotheses are justifiable, as it were. Okay, so the theorem, which is due to Mathern and Tomasco, states the following. So the minimum generating set for R in alpha, provided the prior hypotheses broadly falls into one of three categories. Just kind of briefly outline. So just to be clear again, we are thinking G is a cycle graph, R is the bivariant polynomial ring, and S is comprised of ideals of that. Okay, so the minimum generating set in this setup falls into one of three categories. So the first is if alpha only takes one value. Okay, so this is the case where, okay, I have my cycle and every single edge has the same label. Then RNP alpha is generated by the all ones vector along with n-1 vectors whose coordinates are homogeneous quadratics. So this is the simplest case, and this is a case where you could probably convince yourself that this is true just from first principle, right? Like if I'm telling you that all of my edges are labeled with the same thing, then really you're looking for tuples, n tuples, let's say, of polynomials for which the difference between subsequent terms in your tuple fall into a singular ideal. And so, yeah, I mean, this one, like, just you could probably, if you stare at it long enough, can convince yourself something like this kind of has to be true, just basically from first principle. If alpha takes two values, then our alpha generated by the all ones vector n-2 quadratic as before, and one quartic. Okay, so if you have your cycle and you're allowing for two distinct edge labels on your cycle, then the splines are going to be minimally generated by the all ones vector, n-2 vectors, which are quadratic in every coordinate, and one vector that's quartic in all the coordinates. And finally, otherwise. So that's to say, like my labels can take anywhere from 3 or higher many labels. Otherwise, it's generated by all ones, n-3, n-3 quadratics. N-3 quadratic, and 2 cubes. Okay. So insofar as the proof of this theorem, and just to be clear, I really do encourage everybody to go to the Mather and Tomasco paper, because like they are way more explicit than this. I mean, they literally get their hands dirty and are like, this is what the generators look like. And it's this like wild polynomial expression that's kind of broken down in terms of these coefficients here. So everything is extraordinarily explicit for them. But the reason that, I'm not writing those fully detailed expressions out is because I don't think it's entirely relevant to get all that detail. Really, like for me and for the rest of this talk, what's most significant is just how uniform this answer is. Okay, it's like, again, I don't, in some sense, super duper care about what these ideals are, right? I mean, yes, the coefficients A will appear in the descriptions of these polynomials, but if you kind of take a fuzzier look, if you zoom out a little bit more, right, it's always, in that case, the all ones vector with n-1 quadratics. And in this case, it's always the all ones vector n-2 quadratics and a quartic. And in 3 and higher, it's always, et cetera, et cetera. The descriptions of these generating sets are entirely uniform in a sense. Okay. Okay. Now, when you look at this, as I said, this case especially, right? If you look at this for long enough, you can almost certainly derive the first case by first principles just by being like, well, a cycle is pretty straightforward. I mean, it's just like, boop, 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 boop. It doesn't do much of anything. So you might be like, oh, I see. It's like if every edge has to be labeled the same thing and you're in a cycle. So, you might be able to combinatorics your way out of the problem. Just purely first principles, nothing super fancy. And then you're like, okay, so maybe the truth here is really just like a compactness issue or a large law of small numbers issue where the cycle graph is just too simple to have any like deeply strange behaviors. So the theorem that I'm building to is going to argue that, in fact, no. That this type of like uniformity in presentation is going to be true across essentially all graphs. Now, to make what I just said precise, we're going to need a little bit more. But before we get to that, does anybody have any questions about this kind of somewhat motivating theorem? Yeah.
Should it be easy to see why dimension is always n?
So, is it easy to? You mean like
Is it like an easy argument that you justify that?
Let's see, an easy argument for why we would expect the dimension here to always be n. I don't, especially like if we're allowing for like arbitrary labels, like maybe in the case where once again alpha only takes on one value, we could convince ourselves that the dimension here is going to be n. Why is that?
Can we explicitly just generate this in that case as all ones and then like a vector which has something at one coordinate and zeros everywhere else?
But then if you do that, you're not going to get the edge condition. So yeah, so I guess all this to say is like, no, actually, I don't think just immediately once I've set up our assumptions here, I don't immediately see an easy way to be like, oh, the dimension is going to be n regardless of what form we take. Yeah.
We're assuming that cycles here have n vertices.
Yes.
And no like double edges.
Correct. Yeah. Cycles, yes, cycles and perfect. Okay, so again, my hope is to convince you that this theorem has a moral generalization to just all graphs. But to do that, there's a couple kind of graph theory things that I need. So first of all, observe the following critical thing, which is that if phi from say G to G prime, you know, label, so G alpha, G prime alpha prime, is a label preserving edge contraction then there is a natural map phi star from alpha prime to, notice the contravariance here, it's going the opposite direction of the edge contraction. And now I'm going to draw you a picture, hopefully, that preempts any questions on. So let's look at an example. So let's bring this one back. So here is an edge labeled graph. 2, 4, 3, 2, 3, 3. Two, 4, 3, 3. So this is what I mean when I talk about an edge contraction that preserves labels. Okay. Now, anytime you contract a subtree of a graph, there's actually a natural way to embed the edges of the new thing into the edges of the old thing. Okay. Basically, I'm like, okay, I contracted this thing. Now let's look at the edges that were not contracted. Like they're unaffected by that procedure. They exist as they did before. So I'm just saying like, okay, contract this middle edge. Every other edge that's still there, just keep its label. So this is an edge contraction that's preserving labels. Okay, now my claim is that this should induce a map on splines going the opposite way. So let's kind of see why that is. And this time I'm not going to draw the edge labels just for time's sake. Or maybe I should. Okay, so what you're doing here, let's say maybe this is 7. Three. Also labeled with 3. 6. I think that works. You got it? I think I got it. Okay, so here's a spline on this graph. Now I want to shoot it forward into the bigger graph. So what's like the most natural way to do that?
Just put the same label on the two.
Yeah, that's exactly right. So here, this vertex, right? This is exactly where the contraction happened. This is the contracted vertex. So here's what I'm going to do. I'm going to uncontract everything I contracted, and I'm going to assign whatever this value is to every vertex of that uncontraction. In this case, 7, 3, 3, 3. Now, I call this natural, and I mean that in the formal sense. It's from, well, hold on, let me do that myself. It's natural in the sense of like it respects composition, right? If I contract an edge and then I contract another edge, like the maps being induced is the same as having uncontracted once and then uncontracted again, or uncontracted both at the same time. It respects composition. All right. So this is the first observation, and this is like a key part. Now, before we state next, let me just quickly throw this at you. So if P is a graph, the genus of G is the quantity G is equal to size of the edge set minus size of the vertex set. Okay, so this is distinct. Like sometimes when we talk about genus in graph theory, we're thinking about like the minimal embedding, like the smallest surface that you can embed the graph into. This is not that. Okay, this is much simpler than that. Literally, what I'm pointing at is, well, a number of ways to think about it, that this is the number of linearly independent cycles in the graph. Or equivalently, if we think of this as the topological space, this is the rank of its pylon. Okay. All right. So now we're ready for the kind of key point here. This is the following. What we've done thus far tells us that for any fixed R S, there is a functor our bullet like this, where GGS is the category of genus G graphs labeled and it's contractional.
Can you remind me, S is just an arbitrary set of ideals?
Yes, so S is a set of ideals coming. For now, that's all it is. Contraction. As we kind of wrote over here, right? So if I have a contraction between an S labeled graph and an S labeled graph, then I get a map. Oh, sorry. From the ring of splines to the ring of splines. So this is literally saying just that the spline, like construction, is a functor from the category of S-labeled genus G graphs and contractions to R-. Now, this restriction where all of a sudden I'm like, oh, fix the genus G. Note that when you perform an edge contraction, the genus is preserved. Always. Right? So this is not like losing anything. The category of all graphs with contractions is stratified by these genome. So I'm just looking at one strata in that category.
You're not allowing the contraction of that loops.
No. For me, an edge contraction is always contracting sub-bars, I guess. Do not allow contractions of loops. Okay, so does everybody see like the kind of formalism on the right-hand board and why that is essentially the left-hand board? Okay. All right, so now, all right, so we have all this formalism. And now you're ready for the theorem. The main technical theorem, which is the term Monto self. And it says that the functor for any Noetherian ring R. And any finite set of ideals S in R. Okay, the theory ring R, finite set of ideals S. The functor of period is finitely generated. What does that mean? All right. So it turns out that just as modules can be finitely generated, you can talk about finite generation for functors so long as kind of you're mapping into an abelian category, which we are doing here. But let me just kind of break down. Concretely, what this means for any fixed S and G, there's a finite list, a universal finite list of S-labeled graphs. G1 alpha 1, G2 alpha 2, dot dot dot, the G and alpha n. Such that for any genus G S-labeled graph, say G alpha, the right here, R2 alpha, is generated by images of the generators the phi star here is a map coming from some contraction. So does this make sense? Again, it's like what I'm fixing, fixed for all time, your set of ideals and a genus G, some number, whatever. With those two parameters, there is a finite list, G1 alpha 1, G2 alpha 2, Gn alpha n. All right, this is a universally described finite list. Such that if you give me any genus G graph and you look at the ring or the module of splines for that thing, secretly all of the generation properties of this thing are actually coming from this kind of finite list that we started with. This is what's meant by finite generation. It's finitely generated in the sense that there's a finite list of graphs whose splines generate splines for all of them.
The genus was one, and you had like eight graphs.
Yes, that's exactly right. So like in the previous, like the cycles are essentially the graphs of genus 1. And so that result was an explicit, like completely concrete realization of this in the genus 1 case.
And so like,
For any genus, it is easy to describe.
Absolutely. Absolutely.
and so-
But to like really get into that, to answer that question, yeah. I'll get into like a very, very brief outline of how this, something like this is written. But yeah, are there any other questions about this? Yeah. Oh, yeah.
Please.
Oh, okay, these spinate set of labeled graphs, are they separating family?
Separating in what sense?
As well. Basically, when we take the unit embedding, you can just look at the values on those and describe fully.
That's correct. Yeah, that is correct.
So in the example, the math and too much go.
Yeah.
So there, the fact that things stabilized after 3 different ideals
Right,
is
so-
like that. I should understand that to mean like the GNs, the biggest N is like the triangle in that case, and then all others come from.
And so like the all ones vector, for instance, is coming from the cycle of one vertex.
Yeah.
And when you think about the mass induced by uncontracting kind of like the single vertex, like you are just always propagating the same thing, right? Which gives you the all ones vector. Yeah. So right, to be clear, it's a single vertex. All right. All right, so outline of the proof. No. So to really roughly tell you what's going on here. Left myself considerably less time than what Alex gave himself to do the outline of his proof. So this either means I'm completely screwed or this proof is way easier. It's probably the former. Okay. Or actually, no, probably the latter. Okay, so the outline of the proof. So here's a theorem. Very classical, very beautiful theorem of Kruskal. And it states the following. So if P1, P2, dot, any infinite family of genus C graphs exist I less than j such that GI is an edge contraction equivalently. You can also view this equivalently. The ideals of the coset, well, it's not the coset of graphs with contractions are all finitely generated. I guess genus G. Now, Kruskal, in his original work, it's Kruskal's tree theorem. So his original work, like if you read the papers, he's talking about families of trees. But going from that to this is not terribly hard. So this is basically Kruskal's tree theorem. So yeah, the ideals of the poset of graphs with contractions are all finitely generated. So the idea is that Miata, Proudfoot, and myself categorified critical tree theorem. So a theorem statement about materiality for functors from the category of the idea is like you have critical tree theorem, which is a combinatorial theorem. And what I'm telling you is that work of Miata Proudfoot and myself kind of categorified critical tree theorem to a statement about the theoreanity for functors from the category of these two graphs. So the punchline of all of this is, well, okay, first we have to take this stuff and kind of allow ourselves to incorporate edge labeling. That's not terribly difficult, just some kind of technical details to check. And then we have to realize the module of splines is naturally sitting inside of some module that is obviously finitely generated as a functor from this category. And then the theoreanity tells me submodules of finitely generated modules are finitely generated. And so that is kind of the outline here of how this proof kind of functions. So you ask about, like, do we know anything about the generators in any other case? And the answer is a profound no, because ultimately this finite generation statement follows from what is effectively in the theoreanity. It is an existential. There exists a finite generating set with no actual like detail about what those generators look like. But it turns out that just having finite generation gives you stuff about the overall shape of these modules if you kind of get far enough into the family. Now, what do I mean?
This is much more, right? Because we're thinking about the example of cycle.
Yeah.
I mean, up to contraction,
Yeah.
you reduce everything to two.
Yeah.
However, the theorem from before, one need to have three cases, right?
Right.
Not just one. So it's a little bit richer than.
Oh, yeah, yeah, absolutely. So let me build up to another consequence of this theorem. So definition, a planar rooted tree is a tree with a choice of root vertex okay, as well as a well-ordered on every outgoing edge. From every verse. So in other words, something like this. This is a planar rooted tree. It is a tree. I have chosen a root vertex, and by drawing it in the plane, I have effectively said, okay, this edge is less than this edge, and this edge is less than that. Now, just to be clear, this is not the same thing as this. These are distinct planar rooted trees. Because obviously I've chosen a different well order when I did it. Okay. So here's the theorem. again follows as a consequence, though not in an obvious way, from the technical theorem we stated before. Okay, so let R be A adjoined to X7 mod into the R. So here, this is the kind of irrelevant ideal. So this is my ring. I'm taking a quotient by some power of the irrelevant ideal. Okay, so now I'm going to define Hilbert's for you, HT of T. And it's defined as follows. This is going to be the sum. I'm strategically not going to tell you what the sum is over. Of the dimension over K of the ring of generalized splines times T to the number of edges. Where here, the sum is over planar S labeled trees. So this is my kind of the sum is over planar S labeled trees. Okay. And what the theorem says is that this thing here is actually algebraic as a power system. So I want to illustrate this in the absolute simplest case, because even in the absolute simplest case, what comes out the other end is kind of beautiful. Okay, so let's say that S is the dumbest thing you can do. Is that? Okay. Okay, so if this is my S, regardless of what R is, what is the dimension of the ring of splines? 1, right? Because the only splines are the constant splines. Okay, so this Hilbert-Dietz series becomes the sum over G alpha of just T to the number of edges in G. Okay, put another way, this is the sum over N of the number of planar S labeled, or I guess there's no S anymore, planar trees on N edges times T to the N, just gathering terms. Everybody okay with that? What is the number of planar trees on N edges?
Cadillac.
This is a counting problem. We can do it, come on. It's not an easy counting problem, but
Catalan number?
it's the Catalan numbers. Everybody knows that the generating function for the Catalan numbers is very function. So being that this is a combinatorics talk, I couldn't resist having the Catalan numbers appear out of nowhere. So as is traditional. Okay, anyway, so that's thank you.
Please, is there any comment, questions?
Yeah.
This last part is kind of consistent of Salmon's story, the cooperative bases for.
That is correct, yes. So the way that you prove this is essentially you prove that the category, well, you prove that this category of planar rooted trees is lingual, but it's lingual in like according to a unambiguous context-free language, particularly like there are pushdown automata that appear, and you have to prove it there. So yes, the approach to proving this particular theorem is through that sense of proven language. Yeah.
Now, maybe what, the URL structure of our email.
Great question. So that is in terms of like, because you're right. If you take, I kept calling it the module of splines, and all the time I kept accidentally misspeaking and saying it's the ring of splines, is because there is a ring structure on splines. Now the hard part is that somehow modules over categories, or categorical modules as it were, are pretty, like we have a lot of tools for dealing with them. But then as soon as you start talking about algebras over categories, that becomes a complete disaster area. Where things you want to be true are false, but then they're sometimes true, but then there's like degrees, gradients of truth. So insofar as treating the ring of splines with this categorical language, it's like, it's unclear whether it's going to work out. Yeah, the infrastructure is just not quite there. Yeah.
Well, some of Ruby is just better.
Yeah.
The dimension should be very like some of the dimensions of the labels. How the root pick up and for when to follow the lead them or they're not.
It's so
Because there are no loops, like you're not going to run into issues and it's that.
correct. So like the case of trees is certainly like easier or made easier by the fact that there are no loops. And so like there's a way to describe the tree spline structure inductively in terms of kind of paths from the root. That is correct. But the fact that if you kind of gather all of the dimensions involved and kind of put them in the generating function, the fact that what pops out the other end is algebraic, as it were, does not immediately follow from that description. Yeah.
Right, so, is, since you have base and classify the generating function sometimes to get it asymptotic for
Yeah.
the dimensions?
Yeah. So in terms of like one of these yeah. So in terms of like what are the possible asymptotics for these particular generating functions? Yeah, again, so what you find is that in these cases, just because we are coming from a place of trees, like all of the examples that we've been able to formally work out, I think like asymptotically look similar to the Catalan case. So you only get kind of square roots coming square, yeah. But it's unclear to me whether that's just because of my lack of imagination or whether it's something.
Thank you for coming. We'll resume tomorrow at